Hi and welcome to this tutorial. This one is to hopefully help you understand some questions that could be asked over identifiable properties. So what can I use to separate a mixture? Okay, so question. Which of the following is considered a pure substance? Granite? Nope, granite's a mixture, guys. And how do I know? Because not all granite's the same. If you ever seen any home improvement stores, they're very pretty. Sodium chloride? Well, sodium chloride is NaCl. It's always NaCl. Muddy water can be different. Milk and magnesia can be different. So a pure substance, notice it is also a compound. So a pure substance can be a compound or an element. That's when you understand it. Physical properties of a mixture. A, vary with the amount of the substance. B, depend on the volume of the substance. C, depending on the organization of the substance. Or D, vary depending upon its components. Well, the correct answer is dependent, vary on its components. Because you can have a brownie mixture and it could have walnuts, but you could have another brownie mixture and it doesn't have walnuts. Do you get what I'm saying? So the physical properties of a mixture, they're both brownie mixes, but they vary depending on what it's made up components. Examples, moving a little too fast. Examples of physical properties that depend on the quantity of a substance include boiling point and color. The boiling point's always the same, guys. It doesn't matter. It just seems like it boils faster because you have less of it, but it's still boiling at the same temperature. Color and density, density doesn't change. Melting point and solubility, melting point doesn't change. Oh, there we go. Quantity of a substance. I can have different masses, different volumes of a substance, guys. That's the correct answer. So the physical properties that depend on the quantity of a substance include volume and mass. Okay. Mixtures can have the same composition throughout. Have physical properties dependent on its components. C, have the same physical properties as compounds. Well, that one's false because they aren't going to be the same. And they aren't going to have the same composition throughout. Because when we're talking mixtures, we're talking a broad class, not just the mixture that's sitting in front of you. Okay? And they cannot be separated into their components. A mixture can. That's one of the definitions of a mixture. So mixtures have physical properties dependent on its components. Compounds. Okay, compounds are the same as mixtures. No, they're not, guys. They're not. They cannot be separated by their physical properties. And they can contain more than one element. Sodium chloride, H2O, those are all examples of compounds. So the correct answer, the only answer left, are different kinds of atoms chemically combined with each other. And that's why we can't separate them through physical means, guys. We have to add some energy there to break some bonds and rearrange. White gold is used in jewelry and contains two elements, gold and palladium. A jeweler has two different samples that are both identical in appearance and have uniform composition throughout. What can be said about these samples? Okay, they're two different samples, they're identical in appearance, and have a uniform composition. So that means they're the same, right? So, hetero would be wrong. Okay, the samples have a variable composition. No, we said they were identical appearance and uniform composition. So they are homogeneous mixtures and can be classified as metallic alloys. Okay, pictures about chromatography. And chromatography, just for those of you who don't know, is a way we can separate mixtures. A student is given an unknown substance and used to perform paper chromatography and asked to perform paper chromatography to determine whether it is a mixture or pure substance. She places several drops on the substance on the paper. Her results are below. Notice here, guys, we have different colors. That should clue you in that we're not talking about a compound because number one, we can separate it by physical means. Chromatography is a physical separation. Okay, and number two, so it's a physical separation, and because there's multiple colors, we have a mixture. She has a mixture because there are multiple colors. There you go. That's probably the answer. She has one substance. No. The substance experiment is inconclusive. Actually, this is what the experiment is supposed to do, so it's not inconclusive. And chromatography, yes, it is. Actually, it's very good. It's used all over the place. So it's a good. When a pure solid substance was heated, it changed into another solid and a gas, each of which was a pure substance. Based on these observations, the original solid was A, not a single element. B was a compound. C is a compound, and the products are elements. D was a mixture of two other substances. Well, it wasn't a mixture because it was a pure solid substance. The original solid maybe was not a single element, but what we know for sure is it was a compound. Okay? A brass alloy contains 66% copper and 34% zinc. It is best described. Well, a brass alloy, what is it? You've got to think about this. It's not a pure substance, is it? Is it? No. Is it a compound? No. It is separable because zinc and copper have different conductivities? No. It is a solution because it has the same composition throughout. And that is the definition of a solution, guys, that it has the same composition throughout. Key thing to know. Again, I hope you're learning. It's very important that we learn as we do, guys. Okay, which of the following is an example of a heterogeneous substance? Hetero means different, okay? So we're looking for something that's different throughout. So bottled water is always H2O. Table salt is always NaCl, so it's not different throughout. Pieces of copper are always going to be the pure element Cu, so it's D, candle. And again, all I did there was just use my basic knowledge to figure that one out. Okay. Which of the following are example of a heterogeneous substance? Well, calcium carbonate is an actual compound, and it's always pure. Sodium sulfate, again, pure throughout. Aspirin, pure throughout. Leave salad dressing. Salad dressing would be an example of heterogeneous. And one way to think about that is what happens to salad dressing if you don't mix it up? It's going to... What's it going to do, guys? It's going to... Okay? It's going to do what? It's going to settle down and it's going to be different. Okay? Which of the following is an example of a heterogeneous substance? Again, we're talking about hetero, different. Teflon is the same. M&Ms, are they always the same? Do you always get the same mixture? Vitamin water and red Kool-Aid beverage. Now, this is really a bad question because if you make red Kool-Aid, sometimes it's all settled on the bottom, so it's not really heterogeneous. But for the purposes of this question, M&M candy is our most obvious heterogeneous mixture. Okay? Okay, again, hetero. What does hetero mean? It means different. Which of the following are example of a homogeneous? Homo is the same. Homo equals same. Granite is different throughout. Table salt is always NaCl, so that's probably a good idea of what it is. M&M candy we just determined was hetero. Muddy water is hetero. So table salt, which is a compound, would be a great example of a homo, same throughout substance. Okay, which of the following is an example of a homogeneous substance? Correct answer is glass. Why? Because dirt isn't going to be the same throughout. Flowers, you're going to have your colored petals with your stems, your green stems, so that wouldn't make it a homogeneous. An ice cream sundae wouldn't be homogeneous because you have your caramel on the top, if you're me, and your chocolate chip cookie dough down below, so it's not going to be the same throughout. Which of the following is an example of a homogeneous substance? Again, same throughout. Okay, you might not be so sure, but green tea, maybe, maybe not. Let's come back to it. Sandwich, is a sandwich the same bite throughout? Nope, it isn't. How about a chocolate chip cookie? If I take a bite of it, is it the same throughout? Nope. If you've ever seen pine cones, they can have sap on their little pieces like that, and then no sap over here. So, not a good answer. Correct answer, which one is the same throughout? Green tea, homogeneous. Okay. Which of the following contains a homogeneous mixture? So you're looking for a picture where everything looks kind of like the same. It's the same throughout. Notice in sample A, are they an even ratio? No, they're not. Now, sample B, well, they're all black. Are they the same? No, they're not. Same with sample C. Now we come over here, and they're all a black circle bonded to two clear circles. Every one of them is. It is a homogeneous mixture because it's the same throughout. Which of the following shows an example of a heterogeneous mixture? Which of the following shows an example of a heterogeneous mixture? So, start thinking. What do you think the answer is? Okay, hetero means different. Okay, the diagram A is different, so that's a possible. Diagram B, well, that's different too. Diagram C, well, that's different, and they're not even like mixed together, so that even should clue you in. Diagram D, they're all the same throughout. So, A, B, and C. Oh, that looks like that's the correct answer, doesn't it? Because those are all the ones we said were hetero, different types of mixtures. They weren't the same throughout. Which of the following shows a correct example of a heterogeneous mixture? Well, what do we know about a mixture? It's not going to be the same throughout. Okay? Mixture, same composition, so that one's wrong. A mixture, magnet, two separate. That sounds pretty close. Mixture, filtration, one substance. Nope, because we need two. Air, wind, one solution of gases. Nope, again, one. That's our key word to tell us that's different. So our correct answer, a mixture, we could separate it with magnets and have two separate substances. Could I have more than two? Yes, but I would have two separate substances, definitely. Which flow chart correctly describes a homogeneous material? Homo, same. Okay? Same. So that means it's going to do everything at the same. It's one thing. Okay? You have an unknown, you filter it, you get two substances. That wouldn't be homogeneous. Unknown density and layers. Layers mean different material, so that's not it. Unknown magnet, two substance. We already know that's hetero, so we're going to go with D, unknown boiling, and they boil at the same temperature. That would be a homogeneous material, like water. Okay, filtration can be used. Filtration can be used to separate A, solids from solids. That doesn't make sense, does it, guys? Because how could you use filtration to separate solids from solids? You can't. Liquids from solids, that's a pretty good clue. Liquids from liquids, nope, that's distillation. Liquids from gases, no. Correct answer, filtration can be used to separate liquids from solids. One common method used to separate dyes is, we saw that in the picture, guys, remember? What did we call it? Okay, it's chromatography. Filtration is liquids and solids. Distillation is separation of liquids. Liquid and liquid conductivity would just be how well does it conduct electricity. So that would leave chromatography. Okay. Melting points can be used to separate because A, substances melt at different temperatures. That sounds like a really good one, right? Molecules vibrate rapidly when heating. Is that talking about separating or doing anything like that? Nope, it isn't. Heat causes molecules to, no, molecules do not disintegrate. Many substances fuse at melting point. Nope. We want to separate them. So a substance melts at different temperatures. That's our correct answer. Distillation is a good separating Distillation is a good separation technique for A, solids. Nope. Remember, we've already talked about this a couple times. And we know it's not solids. It is liquids. Distillation is a good separation technique for liquids. And again, solid alloys, why would you, it's asking the same thing. Gases, no. Okay, again, distillation is a great separation technique for B, liquids. Solubility is a good separation technique for, so how soluble is something? Pure metals? No. Okay. B, noble gases? No. C, different salts. There you go. Because solubility means how does it dissolve in water? There you go. So these three, we're not going to be dissolving them in water anytime soon to try and separate them. So the best way to try a good the solubility is a good separation technique is for difference. Magnetism is most beneficial. Well, think about what type of elements are magnetic. Okay. So what do you guys think? Start thinking, start thinking. Gases and non-metallic. Well, why would I use a magnet for something that was non-metallic? B, magnetic solids and solids such as sulfur. Well, that's a good idea because magnets would separate something magnetic from each other. Non-metallic, well, if it's non-metallic, it wouldn't separate because it's not going to be magnetic. Okay, D, non-magnetic solids from non-magnetic. Why would you do that? Magnetism is about having magnetic properties. Why would you even use a magnet with something that was non-magnetic? To test it, yes. But the best answer here to separate, beneficial for separating, would be magnetic solids with solids such as sulfur, because sulfur is non-magnetic. Okay, so it would let me separate the two things out. The following graph was made of two liquids being distilled. What observation can be made regarding point B? Okay, so heat was being added in this direction and temperature is increasing in this direction, and that's degrees C. A, the first liquid component is boiling. Maybe, probably, because look, the temperature is heating, then we have a flat, and at a flat point, that means it's boiling. Okay, the second component already boiled. No, because we haven't had a flat spot. The mixture is homogeneous. We know that it's not because we have a liquid that's something still left afterwards. Energy is being removed. Guys, remember, we're adding heat, so we're not removing energy. So the correct answer is A, the first liquid component is boiling. Okay. A student has 3 unknown solid metals. Which series of tests would be most appropriate used to distinguish among the metals? What do you guys think? Boiling point, density, and color? Can we really melt? I mean, we can't be boiling metals. Color, density, and mass, that's probably not going to tell us much, is it? Okay. Density, mass, and volume. Well, mass, volume, density. Okay. Conductivity. Yes, how well it conducts electricity. Density is great. And color. These are the ones that are most appropriate to distinguish among the metals. Density will help me identify. Color will help me identify. And conductivity will help me. Mass and volume, you guys, not all metals are going to have the same mass. It depends on the amount or the volume of the substance that you have, right? So if I have a different amount of volume, then another sample, I might think I have one thing if I only base my judgment on that. Okay? A student has a mixture of sand, water, salt, and iron pieces. Which procedure would separate the mixture? Okay, we have this. We have magnet. We can separate, so evaporate the water, use a magnet to remove the iron. No sand. Sand. What happened to the sand? So this isn't good. Filter the water to separate the sand. Use a magnet to remove the iron. That's good, but it's not, because what about the water and the salt? We didn't address those. Filter the sand and the iron from the water. Use a magnet to remove the iron from the sand. Evaporate the water. That addresses everything. So this is probably our correct answer. So let's just double check. Let's read. Filter the sand and iron from the water. Okay, the sand and iron are still together, so that doesn't work. Okay, because we didn't separate the sand and the iron with the magnet. So the best answer that would separate this mixture completely is first filter the sand and iron from the water. Use a magnet to remove the iron from the sand, and then evaporate the water to separate the salt. Which of the following observations could be used to separate two metals? A, bubbles form when the substance is dropped into water. Guys, have you separated them? No. How can I use the color of both metals being gray to separate? Won't work. One metal is attracted to a magnet. That's a great way to separate. The volume's not going to tell me anything. It's not going to separate them. So the correct answer is one metal is attracted to the magnet. Guys, I hope this short tutorial helped you out, helped you better understand how to separate mixtures and what is a mixture. So, hey guys, study hard, be proficient, get on.